A friend bought an RTX 4090 for 1,60,000 rupees. His wife thought it was for gaming. It wasn't. He runs Llama 3.170B on it. Another friend tried the same model on an 80,000 rupee laptop, no GPU. It works at 0.8 tokens per second. That's the difference we're breaking down today. A CPU is like having 8 extremely skilled engineers. Each one handles complex logic, branching decisions, varied tasks, brilliant generalists. A GPU is like having 16,000 factory workers. Each one does one simple math operation, but they all work at the same time. Why does AI need all that parallelism, matrix multiplication? That's over 90% of what happens during inference. Your input vector hits a weight matrix, and for a 70 billion parameter model, that's 67 million multipliads per layer. A CPU does this in millions of tiny batches. A GPU? Thousands. Not all GPU cores are equal. Modern GPUs have tensor cores, specialized circuits built specifically for matrix multiplication. An RTX 4090 has 16,384 CUDA cores, but also 512 tensor cores that do the real heavy lifting for AI workloads. Here's the counterintuitive truth most people miss. Inference is usually limited by memory speed, not compute speed. The model weights need to be read from memory for every single token generated. A 70B model in FP16 is 140 gigabytes. For each token, the GPU reads through all 140 gigs. Let's do the math. Token generation time equals model size divided by memory bandwidth. An RTX 4090 at 1008 gigabytes per second gives you about 7 tokens per second. An H100 at 3350 gives you 24. But a CPU with DDR5, 200 gigabytes per second. That's 1.4 tokens per second. Now you see why GPUs win. But there's a hard wall, VRAM. That's the GPU's dedicated memory sitting right next to the cores, which is why it's fast, but it's limited. An RTX 4090 has 24 gigs. Llama 70B in FP16 needs 140 gigs. It simply doesn't fit. When the model doesn't fit, you have 3 options. Quantize it, reduce precision to shrink the model. Offload layers to CPU RAM much slower, or split it across multiple GPUs. Even quantized to 4-bit, that 70B model is 35 gigs, still too big for one 4090. Now here's the wild card, Apple Silicon. M-series chips have unified memory. The CPU and GPU share the same RAM pool. An M2 Max with 96 gigs of unified memory can load a 70B quantized model entirely in GPU-accessible memory. With 400 gigabytes per second bandwidth, that's 10 to 15 tokens per second. So when should you actually use a CPU? Small models under 7 billion parameters, batch processing where latency doesn't matter, and edge devices like a Raspberry Pi running a 1B model for text classification. For anything bigger and real-time, you need a GPU. Let's talk money. A cloud GPU instance is about 15 times faster than CPU at only 1.7 times the cost. Per token, GPU is almost 10 times cheaper. The math is clear. For AI inference at scale, GPU wins on both speed and economics. Want to benchmark your own hardware? Install Llama, then run Llama Bench with set to 0 for CPU only, or 99 to offload all layers to GPU. That flag, number of GPU layers, is your main tuning knob. More layers on GPU means faster until you run out of VRAM. Here's what to remember. GPUs win because of memory bandwidth, not just core count. VRAM is the hard constraint. If it doesn't fit, performance tanks. Tensor cores do the real AI work, and Apple Silicon's unified memory makes it a surprising contender for local inference. Next up, Episode 9, Quantization. How people squeeze 140 gigs into 24 gigs of VRAM.